Hi everyone, today we are going to present about magnetic field. Our team member is Muhammad Hakimi bin Mansor, B0821100035, Shazrah Adnin binti Husin, B0821102211, Najwa Syuhada binti Raizu, B0821104555. For introduction, a magnetic field is a vector field that delineates the magnetic impact on mobile electric charge, electric current and magnetic materials. When a charged particle in a magnetic field is set into motion, it encounters a force perpendicular to both its own velocity and magnetic field. Magnetic field envelope magnetized material, electric current and time-varying electric field. Given that the intensity and direction of a magnetic field can vary across different locations, it is expressed mathematically through a function that assigns a vector to each point in space, referred to as a vector field. Both magnetic field and electric field are interconnected components constituting the electromagnetic force. The basis of measurement for magnetic field strength is Tesla. For magnetic illustration, there are two categories, which magnetic field vector and magnetic field line. Magnetic field vector is a set vector that is drawn on a grid assembled in numerous arrows. The length varies according to the strength of the magnetic force at each specific spatial coordinate. Then direction is point same as compass direction. For magnetic field line, it is a vector quantities and there is an alternative way to represent information consists in magnetic field. Next, it is specified as magnetic force direction on the nodes monopoles at very conceivable point. The magnetic field line becomes an insightful representation offering an intuitive understanding of the directional tendencies of the magnetic force within the field. The magnetic field vector has magnitude and direction of the magnetic field, while line has the direction of the magnetic field at a given point that is indicated by the direction of the field line at that particular location. The picture shows clearly the arrows of magnetic field of each magnetic field vector and magnetic field line. Vector field mathematically denoted by the vector quantity, which line is the measuring line, to visualize the direction and strength, which the closer the line, the stronger the field is. Alright, this is 4 important things that we should know about the magnetic measuring, which is magnetic flux density, magnetic field strength, magnetic flux, and magnetic permeability. Magnetic flux density is the strength of magnetic field at a specific location in space. It means that to measure how strong the magnet is, then the higher magnetic flux density, the stronger the magnet. The unit SI that we use is Tesla or Coulomb. Next is magnetic field strength. Magnetic field strength is symbolized by H. There is the intensity of magnetic field is determined by the magnetic field strength within the material. So you imagine that you have a strong magnet, then it can attract and repel for a greater distance. Why is greater distance? It's because it have a strong magnetic field strength. Alright. Ampere per meter is the unit that we use. Next is magnetic flux. Magnetic flux is the total magnetic field passing through a surface. For example, this is a surface and this is the magnetic field. And when the magnetic field passing through to the surface, then we call it the magnetic flux. The unit that we use is Weber, BW, and lastly is magnetic permeability, which is respond to an applied magnetic field and allow magnetic field to pass through. It means how easy the material allow the magnet to pass through it. Alright, next we talk about the magnet. As we know, the magnet have two poles, which is north pole and south poles. So the direction of the magnetic field is from north to the south. So the closer of density line, the closer the magnetic field. And permanent magnet made, as we know, permanent magnet is made from the material is like iron, cobalt, certain alloys such as neodymium magnet.
Today I will present about the magnetic field created by the current carrying conductor. Okay, for this this magnetic field created by the current, Ampere proposed that the electric charge motion always produce a magnetic field. The current pass through the conductor, it will produce the magnetic field in direct proportion. Okay, next, the magnetic field will be weakened when we increasing the distance between the object and the wire, which described in the Ampere law. Okay, next for the right hand grip rule, we have two cases to apply the right hand grip rule. So for the first case, we use when to determine the magnetic field direction created by the current in wire to determine the direction of current given the magnetic field created by the current. Okay, so the real purpose for this case one, we want to find the direction of the magnetic field and the current. So how to use the right hand grip rule case one? Imagine that you have the straight wire and this is your thumb's right hand grip rule. So this thumb will point the direction of the current and this curved finger will show the direction of the current of the magnetic field. Okay, so your current will go like this and the magnetic field direction will go like this. Okay, next we want to determine the case number 2. We use when to determine the probability of magnetic pole from a coil to determine current direction given the probability of magnetic pole of solenoid. So the real purpose for case number 2, which is we use when to find the direction of magnetic field and current in the coil. Okay, imagine this is your coil and this right hand grip rule, this thumb will show the north pole. And for this curved finger, we show the direction of the current. So your current will go like this, and the direction of magnetic field is from north to the south. So direction of magnetic field will go like this. So that's all for the right hand grip rule. Which is there are two different cases when we want to use to determine whether in the coil or straight wire. Okay, after we have learned about the right hand grip rule, which is to determine the direction of current and the magnetic field, we can use the Biot-Savart law and Ampere law to find the strength of the magnetic field. Okay, so the Biot-Savart law describes the relationship between a small element of current and the magnetic field is produced at the specific point. Direction of magnetic field at the point is perpendicular to plane that formed by the current and the vector is pointing from current to the observation point, which is determined by the cross product rule in the formula. Magnitude of the magnetic field is inversely proportional to a cube of distance between the current and observation point. It is applicable to a steady current in the conductor and used to calculate the magnetic field around the straight current carrying wires. So this unit used is Tesla. Next is Ampere law. The Ampere law relates with the magnetic field around the closed loop to the total current passing through the loop. Direction of line is integral is along closed loop paths and is measure the magnetic field circulation around the loop. Magnitude of line integral is equal to the product of permeability of free space and the total of current passing any surface enclosed by loop. It's useful for calculating magnetic field around the symmetrical shape current carrying such as solenoid and toroid. The unit is Tesla. So this both two is closely related, which is Ampere law and the Biot-Savart. In case where there is a sufficient symmetry, Ampere law can provide the more straightforward way to calculate the magnetic field than the Biot-Savart law.
For discussion, the magnetic field holds immense significance in various domains encompassing physics and engineering. They constitute regions surrounding magnets or in the vicinity of moving electric charge, where the force and magnetism manifest itself. The intrinsic nature of magnetic field entails a consistent directional orientation. It is always pointing from the north to the south pole. The origins of magnetic field are expounded upon tracking back to both permanent magnet and the flow electric current. The application of fundamental principles, particularly the Biot-Savart law and Ampere law, in elucidating the behavior of magnetic field in the context of moving charge. These laws serve as interaction and force experienced by charged particles within magnetic fields.
Alright, lastly, in conclusion, magnetic field plays the important role in natural phenomena and technological application. In physics, they are essential for understanding the behavior of charged particle in motion, such as like we study about the electromagnetism. In technology, magnetic field are harnessed in device. It's like electric motor and transformers. Then understanding and manipulating magnetic field also contribute to advancement in areas such as data storage, energy generation, and medical diagnosis. So I think that's all from our group. Thank you so much for watching.